Hello everyone. This is Dr. Captain K. Sujata, Department of Mathematics and Professor in Mathematics, St. Joseph's College for Women Autonomous, Visakhapatnam. In this session, I am going to discuss characteristic values and characteristic vectors of a square matrix and a linear operator 3. So already I have discussed two videos, discussed two sessions in two sessions about characteristic values and characteristic vectors of a square matrix on linear operator 1 and 2. This is a 3, right? These are the my details. After the session, if any doubts, if you want clarification, then you can contact through my email ID. These are the course outcomes. After successful completion of this course, the student will be able to know and apply the principles of linear algebra, know vocabulary, notation, and operations for matrices and vectors. Find the characteristic equation, eigenvalues, and eigenvectors of the matrix. Now, in the previous sessions, what we have discussed the following points. Definitions on characteristic matrix, characteristic polynomial. Now, what is a characteristic matrix? A minus lambda I, characteristic polynomial, determinant of A minus lambda I, characteristic equation, determinant of A minus lambda I is equal to 0, characteristic root, lambda we call it as a characteristic root, Ax is equal to lambda x for every non-zero vector x such that Ax is equal to lambda x, there x we call it as a characteristic vector. Some theorems on characteristic roots, root and characteristic vector of a square matrix and linear operator we have discussed, and procedure to find the eigenvalues and eigenvectors of a matrix also we have discussed, and problems on eigenvalues and eigenvectors of a matrix we have discussed in the last two sessions, right? Now in this after continuation of the second video, this video will come with the starting with the first problem, that is show that the matrices A and A dash have the same eigenvalues. A and A dash have the same eigenvalues. Now here we are going to consider first this one by known from the matrix identity, right? So did matrix of A minus lambda I whole dash. What is meant by dash means it's a transpose. So A minus lambda I transpose can be written as A dash minus lambda I, because I transpose is nothing but I itself, because that is a unit matrix, right? So we know this is always true. A minus lambda I whole dash is nothing but A dash minus lambda I. After that, we are considered on both sides the determinant. Determinant of A minus lambda I whole dash is nothing but is equal to determinant of A dash minus lambda I. But determinant of A dash is nothing but determinant of A only. Determinant of A dash is nothing but determinant of A. So this is nothing but A minus lambda I only, A minus lambda dash, whereas this is A dash minus lambda I determinant, right? And each one equate to 0. That implies a determinant of A minus lambda is equal to 0. If and only if determinant of A dash minus lambda is equal to 0. This what is the statement? This is nothing but lambda is a characteristic root of A if and only if lambda is a characteristic root of respective matrix A dash. So that A and A dash have the same eigenvalues. A and its transpose have the same eigenvalues. Coming to the next identity. Show that 0 is a characteristic root of a matrix if and only if the matrix is singular. 0 is a characteristic root of the any matrix if and only if the matrix is singular. Matrix is singular means det A is equal to 0. Det A is equal to 0 if and only if 0 is a characteristic root of a matrix. That is A minus 0 I determinant equal to 0, right? So 0 is a characteristic root of A if and only if 0 satisfies the equation determinant of A minus lambda is equal to 0. No, that is if and only if at a time we are proving the both the condition if and only if. That is determinant of A minus 0 I is equal to 0. That is nothing but determinant of A is equal to 0. So that A is equal to 0 means A is singular, right? So at a time we proved if and only if condition. Now next identity, show that the characteristic roots of a triangular matrix are just the diagonal elements of the matrix. Characteristic roots of the triangular matrix are just the diagonal elements of the matrix. So this is a triangular matrix. A is equal to, this is a upper triangular matrix, means lower elements are zeros here. Lower elements becomes a zeros, right? So A is equal to, this is the matrix A11, A12, A13 and so on, A1n. Right now, after that, construct using a characteristic equation. Characteristic root we have to satisfy, no? So the construct characteristic equation, that is a determinant of a minus lambda is equal to 0, right? Then what is the meant by determinant of a minus lambda I? The diagonal elements we have to subtract with the lambda, means a11 minus lambda, a12 same, remaining will be the same, a22 minus lambda, a33 minus lambda and so on, ann minus lambda is equal to 0, right? Now after that, what is that? In the first element, see the previous slide, in the first element, a11 minus lambda, a11 minus lambda, if you take the first row, this is the first row, first element. Similarly, first column, first element, you take the common, that is a11, you take out a11 minus lambda. In the same way, so after that, what will get? This becomes a 1, this becomes a 1. If you take the common, this becomes a 1. So 1, a12, a13, a1n, 0, 0, 0, right? So if we have one remaining elements, whatever these non-zero, but these are the 0 elements, no? These are the 0 elements. So if we have the determinant like that, then we have to consider this determinant equal to determinant of the inner matrix. Determinant of the inner matrix, because these corresponding elements we got a zeros, no? So that's why this determinant equal to, also equal to determinant of this one. Okay. Then after that, again, so take the first, in this determinant, take the first element of the first row, first element of the first column, take it as a common again. That is a22 minus lambda is a common. Already we have a11 minus lambda is there. So a11 minus lambda into a22 minus lambda into remaining matrix. Means yeah, again here this is the one remaining order. No, these are non-zero, these are zeros. Again, this is also equal to inner matrix. Like that, one by one will be eliminated, one row, one column. So finally, all the these factors will come. So final equation as a11 minus lambda, a22 minus lambda, and so on, ann minus lambda is equal to 0. With this, our statement is true. Right? Now coming to the next identity, if lambda 1, lambda 2, lambda n are the eigenvalues of A, so these are the eigenroots or characteristic roots of A, then show that k lambda 1, k lambda 2, and so on, k lambda n, that are the eigenvalues of Ka, right? Now take the given condition, lambda 1, lambda 2, lambda n are eigenvalues of A, right? Now if k is equal to 0, suppose k is equal to 0, in this eigenvector, this is a eigenvalue of A, k is any positive integer here. Suppose if k is equal to 0, what will get? Ka becomes 0. K value 0, no? Ka becomes 0. Means a 0 matrix will get. So each eigenvalue of 0, so because Ka is 0, no? Each eigenvalue of 0 is 0 only. Right? So that implies these are the eigenvalues. 0 in place of k, we have taken k 0, no? So 0 k1, 0 lambda 1, 0 lambda 2, and so on, 0 lambda n are eigenvalues of Ka. Right? So if k is not, the second case is k is not equal to 0. So if k is not equal to 0, what will get? We have consider determinant of Ka minus lambda Ki matrix equation. So determinant of Ka minus lambda Ki. Right? So in this, take the k common. In this, take k common. So what will get? What we want to show? Ka is the k lambda. K lambda is the eigenvalue of k lambda is eigenvalue of Ka. We are proving here. So k lambda or lambda k is the eigenvalue of Ka. We are proving. That's why what we have considered here, Ka minus k lambda I. Ka minus k lambda I from the polynomial. This is nothing but a minus lambda I, no? In the a minus lambda I determinant, in that lambda is a characteristic root of a, right? In the same way, here we want to prove that k lambda is a characteristic root of Ka. That's why we considered this. In this, k, take k common, k into a minus lambda I, k into a minus lambda I, right? No, here this is the determinant of k into a minus lambda I. Actually here a is the n by n, total n, how many lambda, how many eigenvalues we have taken? Total number of eigenvalues of n ra. So how many k's, how many times we have taken? N times. That's the determinant of k. If you want to write down outside, then this becomes a k to the power of n into lambda a minus lambda I, right? Therefore a minus lambda is equal to 0 if and only if ka minus lambda ki is equal to 0. This is 0 if and only if lambda minus ka minus lambda ki is equal to 0. Hence k lambda k or k lambda is a characteristic root of ka, is a characteristic root of ka. This step implies lambda is eigenvalue of a if and only if k lambda is an eigenvalue of ka, right? So means this is, we have proved for one root, one characteristic root. This we can extend up to the n roots also. This is true for n also. Okay. Now coming to the next one, next problem. What is this here? Here A is a non-singular matrix. What is meant by non-singular? Determinant of A is not equal to 0. Okay. Then prove that eigenvalues of A inverse. Eigenvalues of A inverse are the reciprocals of eigenvalues of A. And for every eigenvalues of A inverse means, suppose if we take the eigenvalue of A is lambda. So what we want to show reciprocal annar kada. So ante means 1 by lambda is the eigenvalue of A inverse. That is we want to show. Right? So if lambda is the eigenvalue of A, then what we want to show? 1 by lambda is the eigenvalue of A inverse. Right? Now, what is here given condition? A is a non-singular. What is meant by non-singular? Determinant of A is not equal to 0. What is meant by determinant of A is not equal to 0 means the inverse exists. A inverse always. If that A is not equal to 0, we can construct A inverse. So A inverse exists because A inverse is in the form of, what is the general formula for finding the A inverse? Adjoint A by det A. If det A is not equal to 0, then only, because det A in the denominator, no? If det A is not equal to 0, then only A inverse exists. Okay. So after getting this statement, A inverse exists, then take the lambda, let lambda be the characteristic root of A and x be the corresponding characteristic vector. Whenever if we take the characteristic root, immediately we can construct the characteristic vector satisfying this equation. Ax is equal to lambda x, right? Now already we have taken A inverse exist kada. So that's why multiplying on both sides with A inverse. Otherwise operating on both sides with A inverse, right? Now after that open the brackets for A inverse into A inverse in, no, we can write down the lambda outside, lambda into A inverse x, right? Then A inverse into A is nothing but unit matrix I into x is equal to lambda into A inverse x. Now after that write down the lambda on the left side, right? Ix is nothing but x is equal to lambda into A inverse x. Then write down the lambda on the left side, 1 by lambda into x is equal to A inverse x, right? So that from that A inverse x can be written as 1 by lambda into x. What is meaning of this one? This is in the form of Ax is equal to lambda x, where lambda is a characteristic root of A. In the same way, A inverse x is equal to 1 by lambda into x, then 1 by lambda is a characteristic root of A inverse. Hence, the eigenvalue of A inverse are the reciprocals of eigenvalues of A. Coming to the next one. Show that if lambda is a characteristic root of the matrix A, then k plus lambda is a characteristic root of the matrix A plus ki. Lambda is a characteristic root అని అన్నారు. Matrix A కి lambda characteristic root. అప్పుడు ఏంటిట k plus lambda అనే ఒక characteristic root తీసుకుంటే which is a characteristic root of A plus ki అవుతుంది. A plus ki. So this is in place of A, we have taken A plus ki. So k plus lambda characteristic root of A plus ki. అంటే ఏం ప్రూవ్ చేయాలి? Determinant of A, or otherwise matrix form of A plus ki minus k plus lambda into I into capital X. A plus ki minus, this is a matrix kada, minus k lambda into I, right? So into capital X is equal to, capital X we have to consider is equal to 0. Otherwise, we want to prove that condition, right? Now lambda is the, given that lambda is a characteristic root of the matrix A, let X be the corresponding characteristic vector such that Ax is equal to lambda X, right? So lambda is a characteristic root of the matrix A. Whenever if we take the characteristic root, immediately we can construct the characteristic vector satisfying this equation Ax is equal to lambda X. This is always true, right? Now what we want to show, k plus lambda is a characteristic root of the matrix A plus ki, A plus ki. This is a statement, right? No, that is nothing but A plus ki into x. Already I told A plus ki into x is equal to k plus lambda into x. This is the identity. This is the equation we want to show, right? So consider LHS. A plus ki into x. We want to prove that this is equal to this, right? A plus ki into x can be written as ax plus lambda ix, right? Yeah, this can be written as lambda ki into x. A plus ki into x means ax plus ki into x. Ki into x can be written as only simply kx, simply kx. But ax is nothing but lambda x. Ax is nothing but lambda x, right? So from that lambda plus k into x, lambda plus k into x, right? Therefore k plus lambda. So this is nothing but, so we got finally k plus lambda into x. Therefore k plus lambda is the characteristic root of a plus ki, right? This is the identity. So another identity, that just like previous one, if alpha 1, alpha 2, alpha n are the characteristic roots of the n square matrix A, of n square matrix A, and k is a scalar, right? Then prove that characteristic roots of A minus K are, characteristic roots of A minus Ki are alpha 1 minus K, alpha 2 minus K, and so on, alpha n minus K. So we want to prove that these are the characteristic roots of this matrix. Already characteristic roots alpha 1, alpha 2, alpha n are the characteristic roots of A, the matrix A. So using this, we want to prove that these are the characteristic roots of the matrix A minus Ki, right? So take the given characteristic roots. So for every characteristic roots, there exists a characteristic vector. X can be written as, and satisfies this equation, Ax is equal to alpha Ix. This is not a single characteristic root. No, they are given n. That's why we have taken alpha I, where I is equal to 1 to n, right? Now what we want to show, alpha I minus k are the characteristic roots of A minus Ki. Alpha I minus k are the characteristic roots of A minus Ki of the matrix A minus Ki. Now that is what we want to show, A minus Ki into x. Ax is equal to lambda x. Lambda is alpha I minus k. A is A minus Ki into x, right? Is equal to lambda into x, right? Now consider LHS, A minus Ki into x. Now here expand it, Ax minus Kix. What is meant by Ax? Alpha Ix into minus Kx. So if you take x common, alpha I minus k into x, right? Hence alpha 1 minus k, alpha 2 minus k, alpha n minus k are the characteristic vectors of A minus Ki. Next one, right? Now prove that if the characteristic roots of A are lambda 1, lambda 2, lambda n, then the characteristic roots of A square. So the matrix characteristic roots, these are the characteristic roots of A. Similarly, we can prove that these are the characteristic root of A square. Very simple. Lambda 1, lambda 1, so same. These are the characteristic roots of A. So whenever if we get the characteristic roots, immediately we can we will have the characteristic vectors, corresponding characteristic vectors of the given matrix A, satisfying the equation Ax is equal to lambda Ix. Ax is equal to lambda x for every I is equal to 1 to n, right? Then now what we want to show, lambda I square. Lambda I square are the characteristic vectors, characteristic roots of A square. Lambda I square are the characteristic roots of A square. Means what we want to show Ax is equal to lambda x, no? So A square x is equal to lambda I square x. A square x is equal to lambda I square x, right? Now consider LHS. Now take LHS. A square can be written as A into Ax. Yeah, Ax is replaced by lambda ix, lambda ix. Now again lambda write down outside scalar. So lambda I into Ax. So lambda I again Ax is replaced by lambda ix. So this is lambda I square x. So therefore lambda 1 square, lambda 2 square, lambda n square are the characteristic roots of A square, right? Coming to the next one. This is the last one. Show that the two matrices A comma C inverse AC have the same characteristic roots. So this is the last identity in this session. Let lambda be the characteristic root of what we want to show that two matrices, these are the two matrices A comma C inverse AC have the same characteristic roots. So first we are going to start with the C inverse AC. Take the characteristic root of C inverse AC. Now prove that same characteristic root for A also, right? Let lambda be the characteristic root of C inverse AC. Means C inverse AC by the definition of the characteristic equation, C inverse AC minus lambda is equal to 0, right? Now prove that lambda is a characteristic root of A, that is A minus lambda is equal to 0 determinant, right? Now consider this. Already we have taken this, no? So consider this. Now consider this. After that in the lambda I, here the second term is lambda I, no? In this lambda I, we are introducing C inverse C. C inverse C. So C inverse C is nothing but I only. So that is, we are splitting that C inverse C in between lambda I, we are taken in between C inverse C, right? So this is nothing but this is also equal to lambda I. There is no change in the value, right? Now after that, on the left side take C inverse common, on the right side take C common. Remaining terms are A. Here A is left over, and here lambda I is left, right? It's leftover term, that is A minus lambda I, right? So this is equal to 0. This is a determinant. Now split the determinant. What will get? Determinant of C inverse, determinant of A minus lambda I, determinant of C. But it again, determinant of C inverse is nothing but C whole, determinant of C whole inverse, whereas here determinant of C, both again multiplication becomes identity matrix, unit matrix. So finally the center matrix. Actually, whenever if we have the C inverse AC determinant, it is equal to C inverse AC, the determinant of C inverse AC is equal to determinant of A only, simply. So whatever the center matrix, this determinant of left side if we have C inverse, right side if we have C. So that determinant, if we want to calculate, it is equal to center of the matrix only, because determinant of C whole inverse into C is nothing but I, right? So this becomes the determinant of A minus lambda F. With this, lambda is a characteristic root of A. Therefore, A and C inverse AC have the same characteristic roots, right? Now coming to the conclusion, in this session we discussed following items. So following what we have discussed, some identities and eigenvalues and eigenvectors, nearly 11 means 6 identities we have discussed of a square matrix.